Welcome to month 3 of the Cloud Architect track. This session is about control surfaces, the engineering levels that separate a Claude Code user from a Claude Code architect. Months 1 and 2 were about using Claude Code interactively. Month 3 is about engineering it as a platform component. By the end of this session, you'll command 3 levers. First, the Claude in the hierarchy, which is how you configure context and constraints at scale. Second, agent skills, which is how you package repeatable workflows into reusable/commands your entire team can share. Third, CD integration, which is how you make Claude a first-class citizen in your Azure DevOps pipeline, reviewing code, generating tests, and enforcing quality gates automatically on every pull request. The thread running through everything is the Selonpe case study, a PCI DSS Level 2 TypeScript microservices platform. Real constraints, real architecture decisions, real pipeline YAML. Domain 3 of the Claude Certified Architect exam covers exactly this material, accounting for 20% of your total exam score. 5 learning objectives drive this session, and they build on each other in a deliberate sequence. The first objective is designing a Claude D hierarchy for a TypeScript and Node JS microservices project. You'll understand how project level, directory level, and user level configuration files interact, how inheritance works, and how to apply overrides correctly across service boundaries. The second objective is creating reusable agent skills, custom/commands that encapsulate your team's specific workflows for code review, test generation, and pre-deployment validation. The third objective is configuring MCP server integrations within Claude Code. This covers permission scoping, secrets management via Azure Key Vault, and the principle of least privilege tool grants. The fourth objective is understanding when to apply plan mode versus direct execution based on the risk profile and scope of a change. You'll also master the print flag for non-interactive pipelines and understand the legitimate and dangerous uses of permission mode bypass permissions. The fifth objective brings everything together. Building an automated Azure DevOps CI/CD pipeline where Claude performs PR security review, generates missing unit tests, enforces a quality gate, and posts structured feedback as a PR comment, all without manual intervention. The Claude mid-hierarchy works on 3 levels, and understanding the inheritance semantics is foundational to everything else in this session. Think of it like CSS specificity or Kubernetes config map overrides. The innermost, most specific level wins. The outermost level provides defaults that apply everywhere unless overridden. The first level is the user level file at Claude.net. This is your personal preferences file. It's loaded first, applied globally to every project you open, and has the lowest authority in conflict resolution. A developer who prefers a particular formatting style or has personal toolpaths they always need can set them here without affecting the shared project configuration. This file lives outside the repository and is never committed. The second level is the project root Claude. This is the shared contract, the file that every engineer in every session, in every service directory will inherit from. This is where you encode your PCI DSS constraints, your TypeScript strict mode rules, and your team norms. Keep it lean. Under 2000 tokens is the target. Bloated root files are a design smell that signals you're overloading a single file with responsibilities that should be distributed across directory level files. The third level is the directory level Claude. MED, living inside a service subdirectory like services payments, Claude in D. This file extends or overrides the root configuration for everything within its subtree. By default, directory level files extend their parent. To replace a section entirely rather than extend it, you use the override marker at the section heading. Without it, the directory file adds to the parent's constraints, not replaces them. The context loading order is always user level first, then project root, then the innermost directory level file. When there's a conflict, the innermost wins. Every file you load adds to your token budget. A developer working inside services payments loads all 3 levels simultaneously, so budget accordingly. Let's make the hierarchy concrete with Selonpe. Every design decision here has a rationale. It's not about filling in a template. It's about making architectural choices you can defend. The project context section exists because Claude needs to understand the business domain to give you useful guidance. Writing PCI DSS Level 2 compliant does more than describe the project. It activates Claude's knowledge of PCI DSS requirements when it reviews code. Writing Azure Service Bus tells Claude how services communicate so it understands the architecture context when suggesting changes. Don't just list your tech stack. Give Claude the context it needs to apply your constraints meaningfully. The constraint section uses deliberate imperative language, never and always, not prefer or consider. This matters because Claude weighs imperative language more heavily when making decisions. Never lock payment card numbers or CVVs, even partially, is a specific testable rule. Be careful with sensitive data is not. The seal on pay constraints cover the three most critical areas for a payment platform: data leakage prevention, injection attack prevention through parameterized queries, and input validation through Zod schemas. The skills section registers your custom/commands by pointing to their directory paths. These paths are relative to the Claude Bendy file. Registration here makes the commands available in every Claude code session for this project. The token budget rule is non-negotiable. The root Claude D should load within 2000 tokens, and the total context per session, including all directory level files, should stay below 8000 tokens. If you're exceeding these limits, the mitigation is to split by service boundary and compress verbose constraints into precise single-line rules. The payment service has stricter constraints than the notification service. That's not a problem with your architecture. It's the hierarchy doing exactly what it's designed to do. Directory level files let you isolate compliance requirements to the services that actually have them. The services payments Claude in D file demonstrates both of the key override patterns. First, the constraints override marker replaces the root constraints section entirely for this directory. This is a deliberate security decision. The payment service must not inherit any accidental permissiveness from the root file. The override establishes a complete set of payment-specific rules. Never log any payment or user data, even in debug mode. Always encrypt sensitive fields before writing to the database with AES 2056 and a stricter interpretation of the no secrets rule. Second, plan mode. Always with an override marker forces Claude into plan mode for every single change in the payment service directory, regardless of what the root Claude says. For PCI DSS scoped code, having a human review Claude's proposed changes before they're applied is not optional. It's a compliance requirement. The Epic Gateway Claude may takes a different approach. It extends the root rather than overriding it. No override markers. It adds rate limiting context and IPA alias constraints that are specific to the gateway's role. The root constraints still apply in full. This is the right call when a service has additional constraints beyond the baseline, not different constraints. The cognitive overhead warning is worth taking seriously. Every directory level Claude Med is another file an engineer needs to understand and maintain. Only add one when the service has genuinely different rules. If you're just adding documentation or context that doesn't change Claude's behavior, put it in a README instead. Plan mode and direct execution are a safety dial, and the question is never which is generically better. It's what risk profile does this specific change have. Direct execution is appropriate for low risk, well-constrained tasks, where the blast radius is small and the change is easily reversible. Adding a single unit test, fixing a typo in a docstring, renaming a local variable. These are the right candidates for direct execution. Claude acts immediately, and you review the result. Plan mode requires Claude to generate a step-by-step plan for your review before any file changes occur. Activate it with the plan command in an interactive session or set plan mode. Always in your Claude. May use it when the diff would exceed 20 lines, when infrastructure files are involved, or when you're working in a high compliance service like payments. The Sale on Pay payment service has plan mode, always precisely because the cost of an unreviewed mistake is high. The print flag transforms Claude code from an interactive assistant into a CLI tool. It outputs Claude's response to stealth without launching the terminal UI. making it composable in shell pipelines and scriptable in CI/CD systems. Every automated use of Claude in a pipeline uses print. The permission mode bypass permissions flag skips all permission checks, allowing Claude to read and write files without asking for confirmation. This is essential for non-interactive CI/CD pipelines. There's no human to approve permissions during a pipeline run. But it's only safe when the environment is properly sandboxed. If the pipeline agent has write access to production systems and you enable bypass permissions, Claude can overwrite any file without confirmation. The rule is scope your MCP file system server to source only and confirm the pipeline agent has no production credentials before using this flag. MCP servers are Claude's interface to the outside world. They extend what Claude can do beyond reading and writing local files. The key architectural decision for each server is what is the blast radius if Claude makes a mistake with this tool. The GitHub MCP server gives Claude the ability to create pull requests, list issues, and add comments. These actions are recoverable. A spurious PR comment can be deleted. Read and write access scope to a specific repository is appropriate. The Azure DevOps MCP server enables Claude to create work items, update pipeline configurations, and fetch build logs. These actions are also recoverable, though potentially noisy. Scope access to the specific organization and project. The Azure Key Vault MCP server should always be read only from CI environments. Claude needs to read secrets to pass them to other tools, but it must never be able to write or update Key Vault entries from a pipeline. If Claude could write to Key Vault, a misconfigured pipeline could overwrite your API keys. The file system MCP server is the most consequential. Write file with access to the entire repository root would allow Claude to overwrite any file in your codebase, including your cloud, UD, your pipeline YAML, and your production configuration. Constrain file system access to PO, SAR, CC only, full stop. The PostgreSQL MCP server provides read-only query access. This is valuable for code generation contexts where Claude needs to understand your schema, but never grant write access to a production database from a pipeline. The overarching principle is least privilege. Grant the minimum tool set that the job actually requires, and never use wildcard tool permissions. Explicit enumeration of allowed tools is the only way to reason about what Claude can and cannot do. The MEP JSON file is where you define the MCP servers Claude Code can access and the permissions each server operates under. Getting this configuration right is the difference between a well-governed automation and a wide open security exposure. The structure is an MC server's object with named server blocks. Each block specifies the server binary to run, optional arguments such as the root path for a file system server, environment variable references for secrets, and a permissions block that explicitly enumerates the tools Claude is allowed to call. Secret injection uses NVVAR syntax. The values are never stored in MCP. JSON itself, they come from the shell environment, which in a CI/CD pipeline comes from the Azure Key Vault linked variable group. This ensures that rotating a secret requires only a key vault update with no changes to the committed MCP JSON file. The explicit tool enumeration in the permissions block is the most important security control in this file. Rather than granting all tools a server offers, you list exactly what your workflow needs. Create work item, add per comment, get build logs, nothing else. If Claude attempts to call a tool that isn't in the allow list, the call fails, even if the server supports it. The file system server's args parameter doubles as its scope boundary. By passing SIR as the only argument, you constrain read and write access to the source directory. The permissions block then explicitly names the allowed paths as SIR. 2 layers of restriction, both necessary. Agent skills are the packaging unit for your team's institutional knowledge. A skill in the file is a system prompt for a specific task wrapped in a reusable /command that any engineer on the team can invoke. Think of it as encoding your senior engineer's code review instincts into a reusable tool. The skill in the format has a front matter block with the skill name and description, followed by a markdown body. The body defines trigger phrases that activate the skill the tool access the skill requires and a numbered sequence of steps for Claude to follow. The output format section at the end is critical. It defines the contract that downstream consumers, like your pipeline's quality gate parser, depend on. Change the output format and you break the pipeline. Skills live in three possible locations. Project skills in Claude skills are committed to the repository and shared automatically with the whole team. User skills in Claude skills are personal and never committed. Organization shared skills can live in a mounted volume or a Git submodule shared across multiple repositories. Registration happens through the skills list in your Claude. Mandate. Claude loads each skill D at session start and makes the corresponding / command available. If a skill isn't registered in Claude, Medi, the / command won't work. The three core skills for the SalonPay platform are review for security and compliance analysis, test for identifying untested code and generating just test files, and deploy check for pre-deployment validation, checking environment variables, scanning for hard-coded secrets, and confirming infrastructure constraints before a deployment proceeds. And the review skill implements a specific, repeatable analysis workflow. It begins by running git diff head to get the current stage changes. Using the diff rather than the full file keeps the context window manageable, even on large code bases. Next, it loads the service level Claude D constraints. This is why your constraint section needs to be specific and actionable rather than generic. The analysis checks for the 4 highest priority issues in the SalonPay context. Parameterized queries, detecting string concatenation in SQL, secret leakage, detecting long uppercase string assignments to variables, Zord validation presence, verifying handler functions call a schema before processing, and absence of any types without justification comments. Each file receives a severity-weighted score, and the skill outputs a structured report with overall score, critical issues with specific file and line references, plus remediation guidance, warnings, and a list of past checks. The output format matters as much as the analysis itself. The quality gate in stage 3 of the pipeline passes the score field from this output. If you modify the output format in the skill MIDI, you break the pipeline parser. Version your skills and treat the output format as a public API contract. A test skill uses a different approach. It treats machine-readable coverage data rather than inferring coverage by reading source code. The workflow starts by running npx just coverage of a JSON summary to produce a structured JSON coverage report. Claude then reads coverage summary, JSON, and identifies exactly which functions have branch coverage below 80%. It generates TypeScript jest test files co-located at sast tests, mocking all external dependencies, and writes them to disk. The final step runs just again to validate that the generated tests actually pass and measure the coverage delta. The SalonPay CI/CD pipeline consists of 4 stages, chained sequentially using depends on. If stage 1 fails the quality gate, stages 2, 3, and 4 don't run. This is the right design. There's no value in generating tests for code that has critical security issues, and no value in posting PR feedback when the build has already been failed. Stage 1 is the security review. Claude reads the TypeScript diff for the PR, outputs a JSON object containing a score from 0 to 100 and a list of issues with severity, line reference, and fix suggestion. The quality gate logic enforces the 75% threshold. Stage 2 is test generation. Claude reads the jest coverage report, identifies undertested functions, and writes missing test files. Jest then validates the generated tests. Stage 3 is the quality gate proper, passing stage 1's JSON output and failing the build conditionally. In the 4-stage architecture shown here, the quality gate check is embedded at the end of stage 1, and stage 2 is gated on stage 1 succeeding. Stage 4 posts structured feedback to the PR via the Azure DevOps MCP server. This makes Claude's findings visible to human reviewers in the pull request interface with severity labels. The pipeline triggers on PRs to the main and develop branches with path filters that limit runs to changes under services or TypeScript files. Running on README edits wastes pipeline minutes and desensitizes engineers to build results. Every stage has timeout in minutes. 5 to enforce the 5-minute SLA and prevent hanging on API slowdowns. The pipeline's first stage establishes the pattern that all subsequent stages follow. Install Claude Code, run it with print, capture the output, and act on it programmatically. Fetch step 0 on the checkout step is essential. Without it, Azure DevOps performs a shallow clone that doesn't include enough history to compute Git diff against the target branch. With it, the full Git history is available. The diff is captured with head C5000 to truncate it at 50 kilobytes. This prevents hitting Claude's context window limit on large pull requests. For most teams, 50 kbps covers the relevant changed code. Adjust this limit based on your typical PR size. The JSON schema in the prompt score 100 issues, severity, line, description, fix is a critical part of the prompt. Without an explicit output schema, Claude might return the analysis as prose, markdown, or any number of formats that a simple Python one-liner can't reliably parse. With the schema, the output is structured and consistent. The quality gate uses Python for JSON parsing, chosen because Python is available on the Ubuntu latest runner without any installation step. The gate with the default of 0 handles the edge case where Claude returns JSON without a score field, fail-safe rather than error. The Anthropic API key is passed in the env block, not referenced inside the script text. This matters. Values in env are masked in Azure DevOps pipeline logs. Values concatenated into a script string are not masked and will appear in plain text in the log output. Stage 2 runs only if stage 1 succeeds. That depends on security win condition, succeeded. Combination enforces this. No test generation for code that fails the security review. The test generation workflow has 2 parts. First, just runs with coverage, about as JSON summary to produce a machine-readable coverage report. The true suffix prevents the stage from failing if existing tests have failures. You want the coverage data regardless of existing test health. Second, Claude reads both the coverage JSON and the source files, identifies functions with branch coverage below 80%, and generates TypeScript jest test files to sarcasts. The prompt constraints. Use TypeScript. Mock external dependencies. Are concise but load-bearing. Without the TypeScript constraint, Claude might generate JavaScript. Without the mocking constraint, generated tests might have real side effects. After test generation, the final step reruns jest with coverage pass with no tests. The pass with no test flag means the stage doesn't fail when no new test files were generated, which happens when all changed functions already have adequate coverage. The 5-minute timeout for this stage is aggressive for large code bases. If you're consistently hitting timeouts, add C2000 to limit the source context pass to Claude. The coverage JSON is compact. The source files are what drives context length. The quality gate logic is the same Python one-liner pattern from stage 1. Pass the score field, compare to 75, exit 1 if it falls below. In production, you'd add proper error handling for malformed JSON, but the pattern is correct. The 4-step keyword integration pattern is the canonical way to handle secrets in Azure DevOps pipelines. Every pipeline that uses Claude Code should follow this exact pattern. Step 1. Store the secret in Azure Keyword using the asKeyword secret set command. Keyword's naming convention uses hyphens. Anthropic API key. This is important to remember because it differs from the convention we'll use in the pipeline. Step 2. Create a variable group in Azure DevOps and link it to the keyword. During this linking step, you map the keyword secret name, Anthropic API key, to a pipeline variable name. Pipeline variable names cannot contain hyphens, so the mapping converts hyphens to underscores. Anthropic API cams Anthropic API key. This conversion is required, but not automatic. You must set it explicitly in the variable group configuration. This hyphen to underscore mismatch is the single most common failure point when setting up this integration for the first time. Step 3. Reference the variable group in your pipeline YAM with group Cylon Pay Secrets under variables. The pipeline variable, Anthropic API key, is then available throughout the pipeline. Pass it to Claude only through the env Lock never by concatenating it into a script string. Step 4. The operational payoff. When you need to rotate the API key, you update it in Azure Keyboard only. The variable group fetches the new value on the next pipeline run. Zero changes to any pipeline YAML file, zero changes to any committed code. This is the architecture that makes secret rotation a 30-second operation rather than a deployment event. The Ceylon Pay Challenge asks you to design and implement the full configuration stack for a real engineering team migrating to a Claude Code Workflow. The 4 deliverables represent the 4 artifacts an architect would produce for this engagement. Deliverable 1 is the Claude MD hierarchy design document. This is the architect's thinking made visible. A hierarchy map showing all Claude B files and their inheritance relationships, documented decisions for the root file with specific rationale, service level override analysis, and a token budget calculation. The token budget analysis is where most participants underinvest. Run word count on your Claude B files, estimate tokens at roughly 1 token per word, and verify you're within the 2000 token root limit and 8000 token session limit. Deliverable 2 is the working repository with Claude, many files, and agent skills. The minimum functionality checklist is your acceptance criteria. The most disqualifying failure mode is having a root Claude D that exceeds 2000 tokens. It means your hierarchy design is wrong. Deliverable 3 is the Azure DevOps pipeline YAML. Validate it with as pipelines run, try run before submitting. YAML syntax errors are an immediate point deduction. Verify that Anthropic API key is never in plain text in the file. Deliverable 4 is the peer review quality report. 3 PR scenarios test your pipeline's detection capability. A SQL injection via parameter concatenation, a hard-coded JWT secret, and missing input validation on a financial transaction endpoint. The evaluation criteria rewards quantified accuracy analysis, true positive rate, false positive analysis with root cause, not just narrative description. Passing is 75%. The path to exceptional requires architectural thinking and constraint specificity. Generic constraints like follow security best practices score lower than specific testable constraints like never concatenate user-supplied input into SQL query strings. Always use parameterized queries via Prisma's query API. 4 recurring failure patterns appear consistently when teams adopt Claude Code at scale. Understanding them upfront saves you the learning the hard way version. The first pitfall is the bloated root Claude melee. When you dump all context, constraints, and style guides into a single file, you create a 500-line configuration that exceeds the token budget, slows every session, and becomes too large for engineers to read and maintain. The best practice is splitting by service boundary. Root Claude be under 2000 tokens with the essentials, service level files handling service specific concerns, total context under 8000 tokens per session. The second pitfall is using permission mode bypass permissions outside a sandboxed environment. This flag removes all safety checks. If your CI pipeline agent has write access to production systems and you're running Claude with bypass permissions, single misconfigured prompt can overwrite production configuration files without any warning or approval gate. The fix is simple. Scope the file system MCP server to see only and verify the pipeline agent has zero production write access before enabling this flag. The third pitfall is wildcard MCP permissions. Setting tools in your respective JSON grants Claude every tool every MCP server supports, including ones you may not have intended to expose. The best practice is explicit enumeration. List only the 3 or 4 tools your workflow actually uses and nothing else. The fourth pitfall is hard-coding secrets in pipeline YAML or Claude files. Even a secret committed and then removed from the code base remains in Git history and is retrievable. The best practice is Azure Key Vault plus variable groups. Secrets live only in Key Vault. Pipeline references use variable name, syntax, and no secret value ever appears in committed files. 5 things to carry forward from this session, your Claude. Meta hierarchy is your system prompt architecture. It's not a configuration file. It's a set of engineering decisions about what Claude knows, what it can do, and what it's forbidden from doing. Design it like an API, specific, versioned, and with a clear contract at each level. Agent skills are reusable, shareable automation units. A well-written skill, MD encodes institutional knowledge that previously existed only in a senior engineer's head. The output format is a public API contract. Treat it as one. MCP servers extend Claude's reach. Always apply least privilege. Enumerate tools explicitly, scope file system access to, say, keep keyboard read only, and audit every tool call in your production pipelines. In CI/CD, the print flag makes Claude a composable CLI tool, and permission mode bypass permissions makes it automation friendly, but only in a properly sandboxed environment with scoped MCP permissions. Secrets belong in Azure Key Vault. The four-step pattern: key vault, variable group, variable name, reference, and where injection is non-negotiable. It enables rotation without code changes and prevents the single most common pipeline security incident. Domain 3 of the exam covers inheritance semantics, token budget limits, plan mode triggers, MCP permission scoping, and pipeline YAML structure. Scenario-based questions will test your ability to reason about configurations you haven't seen before, not just configurations you've memorized. Month 4 takes the foundation you've built today, the Claude, the hierarchy, the skills, the pipeline patterns, and scales it into multi-agent orchestration, where multiple Claude instances with narrow context are coordinated by an orchestrator agent.